Hello again. Thanks for joining us on Space Nuts. This is a Q&A edition. My name is Andrew Dunkley, and it's always good to have your company wherever you are in the world. Today, we're going to be answering questions from our audience, and we've got a question from Tony about Hawking radiation. Stuart has asked a question about something we've never discussed before, or have we discussed it a million times? It's called dark energy. And Thomas wants to know what would happen if we could just, move Earth over there. All of those questions will be answered on today's episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
He's back for more. His name is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you after all that technical hiatus?
Yes. Normally we record 2 episodes back to back with only moments in between, but today it was a very different story. The internet would not cooperate. Space doesn't cooperate either. I think they were in collusion. That left us high and dry, but it gave me time to make a cup of coffee.
Very good.
There it is. So
yeah. I've got one too.
Yes. I love the coffee. I'm a nut for it. So let's get stuck into some questions, shall we, Fred? Oh, before we do, though, we have a sort of an answer to one of our questions. We got a question from Andy in London not so long ago, and we dealt with his interests. But he mentioned that he's a train driver, and I just said, tell us more about your job. Really interested to learn. And he sent us a little bit of info about his job. And I like that we can do this. I think, we've created, or they've created themselves, this interesting environment where a lot of the listeners can talk to each other on our podcast group on Facebook. And it's nice to get to know a few people. So this is Andy, the train driver from London.
Hi guys, this is Andy, the train driver from London. Thanks for answering my question. Much appreciated. Just wanted to get back to you regarding the question about trains. Yeah, so I live in West Sussex, but I actually work near Norwood Junction on the London Bridge line. And I drive 2 types of trains, one electric, one diesel. Both are about 50 tonnes per coach. So longest train I drive is 12 coaches long. And so that equates to about 600 tonnes. The diesel trains, I drive them from London Bridge down to West Sussex to a place called Uckfield. And they've got 1 engine per coach. These engines are pretty similar to like a double-decker bus engine, like 11-litre turbocharged. So longest train I drive down there is 10 coaches. So you've got 10 11-litre turbo engines all roaring away at the same time. Sounds quite impressive. Yep, I've been doing it 22 years, and I'm also an instructor, so I teach all the new recruits how to drive these trains. I also do the DC lines and the AC lines, which are the overhead cables, 25,000 volts. And I drive the electric trains over to Watford up to 100 miles an hour. So yeah, it's a good job. I enjoy it. I also enjoy your podcast. So thanks for everything you do. And I hope that answered your questions. Have a good day, guys. See you later. Bye.
Thanks, Andy. I know that's got nothing to do with astronomy or space science, but I just thought it was so good of him to tell us a little bit about his amazing life and his amazing job. And how many jobs do you know, Fred, where you're allowed to do over 100 miles an hour? I mean...
Well, you're paid to do it as well.
Yeah. What a great gig. Geez, Andy, thanks a lot. That was fantastic. Really enjoyed hearing about you. My next door neighbour's a retired train driver, so I'm going to get him over here and let him hear that, because I think he'd be absolutely intrigued. And of course, there's been a lot of local interest lately because a whole set of new trains are being built in Dubbo for the regional lines. And I actually spotted one yesterday out doing a trial run, and it's very quiet. I thought I heard this sound and went, what is that? And I had a look, and it whispered past. It was really amazing. And Andy would be interested to know, these new trains that they're putting on regional New South Wales tracks are hybrids. So it'll run diesel from here to the city of Lithgow, and then they'll pop up the electric connector and run
Pantograph,
on
it's called.
electric.
Pantograph.
Yeah, and they'll run to Sydney.
Yeah.
On the electric
Well, that's pretty
line, which is awesome. So lots of I love trains. So and Judy's dad was a station master, so we've got a bit of a connection with trains in our family and next door, as it turns out. We better get down to it though, Fred. We've got a bunch of questions to go through, and here's the first one. Hi lads, Shane here from Ireland, and I have a question regarding interstellar comet 3I Atlas. I recently read an article that stated new studies indicate comet 3I Atlas could potentially be nearly as old as the universe itself. This got me to thinking about how a comet can exist for so long, potentially 13 billion years or so, and not burn up completely as it passes through solar systems. Even if it is as large as a few kilometres in diameter, it must burn off debris at an alarming rate for it to have a coma thousands of kilometres in length that can be seen from Earth. My guess is that it has probably spent 99% of its time in freezing interstellar space, but even at 1% of the time spent passing through other solar systems, should be enough to make it evaporate. Love the show. Keep up the good work. Over and out, Shane. Thank you, Shane, and happy St. Patrick's Day, which was yesterday, our time. And all the golfers at our course were dressed in green. So, that was fun. Except me, because I forgot. The interesting question by Shane. Is that a thing, that the 3I Atlas could be that old?
Yeah, it's really interesting that there's new information coming out all the time about how different 3I Atlas is to the comets in our own solar system. In fact, I just saw one while we were off air, as you were desperately trying to fix the interweb there. I saw a news story which is about the water content of 3I Atlas, and it's a ratio of normal to heavy water, which I haven't read yet, but it's again, it's an outlier, just like so many of its attributes are outliers. I haven't seen reports that it might be as old as the universe. It clearly won't be as old as, it has to be middle-aged in the sense that some of the ices that we see in it are complex molecules. There's the sort of chemical mix that we see in the solar system, except they're extremes in the way these, the ratios of one to the other. And for those elements all to be there, you must be talking about a solar system, its origin being in a solar system that is relatively rich in these elements. And that means it's not something in the very early universe where most, there was just hydrogen, helium and iron were the most common constituents. It's got all the sort of array of chemistry or chemical elements that we are used to in the solar system. So I think it's fair to say it's probably old, but I'm not going to hazard a guess on how old it is.
I just had a quick look, Fred, and as at March 2026, according to Live Science, it's possibly 10 to 12 billion years old, they think. That's a lot, isn't it?
That's old, yeah. But you've got to balance that against the fact that it does have, it does have a chemical composition in terms of the elements that are present, the abundances of the elements, that's not too different from ours. But that's clearly something that the pundits are working on. I think the nub of Shane's question is, I think his estimate of 99% of its time being in deep space and 1% being passing through a solar system, I suspect that's probably wildly wrong, because I suspect that it's more like 99.999999999% in deep space and a tiny fraction that would be passing through solar systems. And what makes me say that is that space is big. It's there's a lot of empty space out there, and the solar systems are, yes, they're everywhere. We see them. You know, we can see stars and planets and all the rest of it, but the space between them is immense. And so, I think it's understandable that an object as old as that, let's say 10 to 12 billion years, that could well have been an object that has kept most of its primordial ice. I don't think a lot is going to depend on how near it passes to a star when it's going through a solar system. That's the crucial thing. How much radiation is it feeling from the star? How much of its ice sublimes into space? And it's a fairly small fraction, I think, of the total mass. I have seen work on trying to understand comets in our own solar system in terms of how many times they've passed near the sun and what the sort of mass loss has resulted from that.
Yeah.
But they are falling in from the Oort cloud, so their orbits are quite different from 3I Atlas, which is hurtling through the solar system at 60 odd kilometers per second. It's nowhere near the sun in that regard. So, and it doesn't have a big tail. The images that we see show a short, stubby tail with the coma. So there is material coming off it. I wouldn't like to hazard a guess as to how much. And I don't even know whether there's a reasonable estimate as to what the size of 3I Atlas is in terms of the size of its nucleus, the icy bit.
Yeah.
You might be able to find that out as well.
In terms of diameter, it's 440 meters. Hang on a sec. It's got all sorts of different numbers here. Based on 2025 Hubble Space Telescope observations, the nucleus of the comet is between 440 meters and 5.6 kilometers in diameter.
Yeah.
It's pretty
hard to
big. Yeah.
That's right. Because we don't see the nucleus itself. We just see the coma around the nucleus as it outgasses.
Yeah.
But, maybe when it set off, it was twice the size of that. Who knows? But I think it's an interesting question that Shane poses. But I think it probably all makes sense. I think the numbers kind of add up, even if it is very, very old.
Yeah, I'm sure. And how fast did you say? 60 kilometres a second?
Something like that. Yes, it's in that region.
That's nearly as fast as Andy the train driver.
Well, that's right.
Yeah. All right. So there it is, Shane. Thanks for the question. Hopefully we adequately answered it for you. Our next question comes from somebody else. Hi, Professor Fred and Andrew. My question is concerning Hawking radiation. When two quantum particles pop into existence from a black hole, are the particles entangled? If not, why? Also, you inform and educate us so well, so I thought I would share some remarkable stats I read the other day. The surface of the sun is very noisy. Forget the vacuum thingy for a minute. The sun's surface apparently crackles away at 100 decibels, give or take. The light from the sun takes approximately 8 minutes to reach us. However, the sound of the crackling sun would not reach us for 13 years. I love your show. Tony from Marrickville in New South Wales. P.S. Looking forward to the professor's next Belrose presentation. What's that about, Fred?
Well, we've been doing these for quite a long time. Something called Fred Watson Presents. It's a sporadic thing. We put on a talk. Marnie, of course, the mastermind behind all this, arranges it. We've got a place in Belrose, not very far from where we live here in Davidson in the Northern Beaches. And there's a nice bowling club there. We go on. They've got a room which actually has a great screen, and I give talks from time to time. Once in a while, we get a guest speaker as well who gives a talk. So we maybe do 3 or 4 a year, something like that.
Lovely. Very nice. Well, that's what he's talking about. Those sun statistics are very interesting. You and I have talked about how loud the sun is before, so it's a good thing we can't hear it, or
that's right.
We'd be in trouble. But his question was about Hawking radiation. When two quantum particles pop into existence from a black hole, are the particles entangled? If not, why not? Yeah, so that's the bottom line. And I know you're not a particle physicist.
But doing what you do, check it out on the interweb, and the answer seems to be yes. So, formed together from vacuum energy, these temporary particle-antiparticle pairs share linked quantum properties like spin. And so they are entangled, and that does sort of raise the question, doesn't it, that when one of them's sucked into the black hole and the other one's not, and it radiates outwards, well, they become disentangled then, because they would be they wouldn't be in what's called a state of superposition, which is the quantum state where things can be upside down and the right way up at the same time and things of that sort. So I think they're probably entangled when they and look, I'm kind of making this up, but and some particle physicists might want to correct me, but I think they're entangled when they're formed. But I suspect one of them crossing the event horizon becomes disentangled very quickly.
Yeah, I guess so. We've got about 10,000 quantum physicists who listen to us. So one of them might give us an answer to that. And how does this differ from string theory? Is that nothing to do with quantum entanglement?
So string theory, look, it's still conjectured. It's still not a theory that has any real evidence to support it. But that envisages particles as being like strings, as the name implies. So rather than a particle, what you've got is something with an additional dimension, and that the suggestion is that some of those dimensions are microscopic. They're wrapped up on the external surface of a string. I'm not sure what the interface between between string theory and quantum entanglement is. And it's an interesting thought that you've thrown in there, Andrew. I wouldn't mind reading up a little bit more about that, because it's quite an interesting area. I used to do talks about string theory, most of which I've forgotten. But they were the thing about string theory is you do have to have additional dimensions other than the four that we know about. And a lot of theories postulate additional dimensions. If I remember rightly, string theories had, the numbers were ridiculous. I think some of these theories needed 20 or more additional dimensions. And so it's hard to get your head around where all those dimensions might be lurking. But they're hidden dimensions, basically.
Fascinating. Yeah. Gosh, I think I opened a can of worms.
You did. Yeah, you did.
All right. But yeah, the bottom line for that question is yes. The two quantum particles pop into existence at the same time, but we don't know what happens if one of them gets sucked in. Is that it?
I think that's the bottom line, yeah.
Yeah. Wow. Fascinating. All right. Thanks, Tony. Thanks for the question. Hope all is well in Marrickville. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a break from the show to tell you about our sponsor, NordVPN. Now, if you've ever felt like your online privacy is slipping through the cracks, then you're not alone. Hackers, scammers, harvesters, they're all out there trying to get your private info, whether that's your passwords or your personal details to sell on the dark web, or to use themselves to access your bank accounts, credit card details, and who knows what else. But you can protect yourself with NordVPN. You can take control at home, or more importantly, when you're out in public using free Wi-Fi. Right now, using the exclusive Space Nuts offer, you can receive 4 extra months for free on a NordVPN.com plan. NordVPN encrypts your internet connection, hides your IP address, and offers access to over 7,700 servers around the world. Plus, with features like Threat Protection Pro, MeshNet, ultra-fast speeds via Nord links, your digital life stays private and efficient. So don't miss out. Visit nordvpn.com/spacenuts and enter the code spacenuts to claim this deal. Remember, there's a 30-day money-back guarantee, so it's risk-free to try. Stay safe, stay private, and browse with confidence. That's nordvpn.com/spacenuts.
Zero G, and I feel fine.
Space Nuts.
Okay, Fred, we'll go straight to our next question. This one comes from Stuart.
G'day, this is Stuart from Tasmania, home of the very cute little Tasmanian devil. I just had a question about dark energy and how it's propelling the expansion of the universe. We know it's dark in the sense that it's mysterious, but I was also wondering about the use of the word energy, considering the current theory says that having propelled the universe to expand, the level of dark energy does not decrease in our area, and the new area of space has just as much dark energy in it. I was just wondering how this would be possible given the current understanding of the laws of physics and the conservation of energy. I was just wondering if you could give us an update on the current thinking with regard to all this, and maybe I'm missing out on some new breakthroughs. Thank you.
Thank you, Stuart. Love Tasmania, beautiful place, and I would balk at calling a Tasmanian devil cute. I have seen them devour a rabbit, and they don't leave a thing. They eat absolutely everything: the bones, the fur, and everything in between. They are the perfect, nature's perfect garbage mulcher. Absolutely. So, thanks for the info, Stuart. Fred?
Yeah, it's a great question, and there is new thinking on dark energy. It is counterintuitive that as you make more space, you make more energy, because you've got to come from somewhere. All right, so what's the observation that leads to this idea? It's the fact that all the evidence points to an accelerated expansion of the universe, and that has been known since 1998. We have attributed that acceleration to this phenomenon of dark energy, which is, I always think of it as a kind of springiness of space. And the bigger space gets, the springier it becomes. And that's the sort of standard model of dark energy, which puts a term into some of Einstein's theories of relativity, which he called the cosmological constant. And it was a term that he invented in the mathematics to allow for the fact. In fact, he put it there because before, when he was doing this work, he didn't know that the universe was expanding at all. And so he had to put this cosmological constant in to stop the universe expanding or contracting. He thought it was static. And then when, in 1929, Hubble discovered that the universe is expanding, he sort of regretted that. And he, in a conversation, I think with George Gamow, around I don't know, in the 40s or 50s, he said it was the biggest blunder of his life, the cosmological constant. But when people realize that the expansion of the universe is actually accelerating, then the cosmological constant suddenly became one way of explaining that, or at least modeling what was happening. If it's the cosmological constant that's doing this, then what you've got is an increase in energy that is proportional to the increase in space. So as the volume increases, you get a proportional amount of energy increase. That's because the energy per unit volume is constant. That's where the idea of a cosmological constant comes from. So that has been the model until recently, because we didn't have any observations to support anything else. But as you and I have spoken about, Andrew, the latest thinking, and it comes from the Dark Energy Survey, a major survey of the positions and velocities of galaxies that actually give you some idea of what's going on the big picture side of the universe, looking back several billion years in our time-wise direction as we look out into space, always looking back in time. So the latest thinking seems to suggest that the cosmological constant isn't constant, because it looks as though the acceleration is actually slowing down or reducing. And that's led to conversations that you and I have had, that maybe one day the acceleration would turn into a deceleration, and then we might well return to the era of the Big Crunch or the Gnab Gib. I'll put an aside in here, Andrew, just for your benefit.
Okay.
I can't remember who it was, one of our listeners said the Gnab Gib sounds like one of the Lost Bee Gee brothers.
Yes.
And I told you in the last episode that I was narrating some music in a couple of concerts down in Canberra over the weekend. And I threw that one in, and it went down an absolute treat. So thank you.
That
Was it Martin? Yes, I had a feeling it was Martin. So Martin, thank you for that. You've given me a really...
You gave Fred a joke. He doesn't tell many jokes, so...
Well, actually, most of my talks are one constant joke, I have to say. You've never heard one. Oh, you probably have, actually, a long time ago. But yeah, I do try and throw in as much lightness as I can, and that hit the spot perfectly. So thank you, Martin. I really enjoyed that. Right, back to the story.
Yes.
So there won't be a Gnab Gib, a big crunch, unless the acceleration really turns into a deceleration. And that would modify how we understand, just coming back to Stuart's question, how we understand that, the energy constant of the universe. And I think it leads you to the sort of thing we were just talking about, higher dimensions and new physics we don't understand. I think if the decreasing acceleration of the universe is going to be properly explained, we may well have to invoke new physics that currently are unknown. So this is cutting edge stuff. It's very exciting, and we'll just see where it goes, and you'll probably hear about it on Space Nuts, Stuart.
Yes, it's such a big area to try and understand, and I think we're really only at the dawn of the process of unraveling what dark energy is all about. And we've said before, it's poorly named. It's probably, and it's creating so much confusion with dark matter, which is also probably poorly named. But anyway, Stuart might be interested to go to the darkenergysurvey.org website if he wants to find out more, because there's plenty of information there, and they're updating what they're learning or studying all the time. So, darkenergysurvey.org could be a good port of call for you, Stuart. And have fun down there with your Tasmanian devils. When Judy and I went to Tasmania on our honeymoon, believe it or not, she never let me forget it, one of the most common roadkills we saw were Tasmanian devils, which is very sad. But, there were quite a few of them lying on the sides of the roads, which is... I guess, it's unique to Tasmania. Here it's kangaroos and more kangaroos. Okay, thanks, Stuart. We'll go on to our final question. Hello, Space Nuts. This is Thomas from Virginia. So, and this is a what-if question, Fred. I love what-if questions. So, if you had a way to push Earth to another star's Goldilocks zone when our sun starts to die, what would happen to the atmosphere on the way? I assume it would freeze, but then what would happen to it after that? So, that comes from Thomas. It reminds me of a movie I watched, and I must confess I didn't finish it. It just got too much for me. I love science fiction, but this one just threw me over the edge. It was I can't remember the title of it, but Earth had to move because there was an issue probably with the sun, and they wanted to move us out to Jupiter. And so they attached all these giant rockets to Earth, and it just got crazier from there. But let's say you could. What would happen to our atmosphere?
It's a great question because there are, when you think of gas giants, they've got atmospheres that are still gaseous, well outside the Goldilocks zone. Possibly partly because those bodies are radiating heat themselves, as is the Earth at a very low level. The Earth has some low-level nuclear reactions going on in its nucleus in the centre, at the core of the Earth. And so there is a little bit of heat comes from the Earth itself. that might stop it freezing. So I'm sort of the parallel that I would draw in my head is with the dwarf planet Pluto, which does have an atmosphere. It's very, very thin, but a lot of the kind of atmospheric constituents of the Earth are actually frozen at the distance of Pluto. So I think, what is it, minus 230 or thereabouts, the temperature at Pluto on the surface. The nitrogen is frozen because you've got nitrogen glaciers there and sort of slushy nitrogen flowing around. So I suspect that might happen to the Earth's atmosphere, but there would be a residual level of air, I think. But when you got back to your Goldilocks zone in another solar system, hopefully it would all just come good again. And, your nitrogen starts to be a gas rather than a solid. And you could, there might be some loss of components of the atmosphere, but generally I think what you might have is something much the same as you set off with. That's my guess anyway.
I don't think we have to take Earth that far, though. If, when the sun expands, and we just have to move out a little bit, wouldn't we?
I think that's right. But the problem is, as you said, it's just science fiction to think of moving a planet. We don't have any way of doing that at the moment, other than the only other way to do it will be to hit it with another planet, but that brings its own concerns.
That would work.
Yes.
As we spoke about in the last episode, although...
Yeah, indeed, that's right.
Yeah,
indeed.
Wouldn't be a good effect. Maybe we could employ string theory and just drag ourselves out there.
Who knows? Well, if there's extra hidden dimensions, we might be able to pop the Earth into one of them and come out somewhere else.
Yeah. I think if you did find a way to move Earth to a better place when required, you'd have to put people somewhere else in the meantime. You'd probably survive the journey on the planet itself. Probably not. It's a bit tough. But yeah, interesting question, Thomas. But yes, this South Koreans did make a movie about this very concept, if you want to look it up. I can't remember the name. I don't want to. I didn't really enjoy it. It was a weird film, but they do make weird movies in South Korea, so it's right up there. They love their science fiction, though. Thanks, Thomas. Great to hear from you. And if you have questions for us, please go to our website and click on the Ask Me Anything tab at the top, where you can send us text and audio questions. We're still struggling to get audio questions. People don't want to talk to us, Fred. I think that's what it comes down to. SpaceNutsPodcast.com and SpaceNuts.io are the two URLs that will work. And while you're there, have a look around. And please leave reviews on your favourite podcasting platform. The more reviews, the better, apparently, unless they're, one-starers. Don't really like those, but, you get the occasional one, I suppose. There it is, Fred. Thanks so much. Great to catch up.
It is. Thank you for having me. And sorry about all the glitches earlier on.
It's all good. It's all good.
Yes.
Professor Fred Watson, astronomer at large. We'll catch him on the next episode. And thanks to Hugh in the studio, who couldn't be with us today because they called him out to fix the internet. So he'll be back in about 300 years. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.